everybody. So today we're going to combine your two favorite things, stoichiometry and gas laws. I know it doesn't seem like it could get so good, but it's getting this good. Okay, so we're going to be doing gas stoichiometry. And gas stoichiometry is used to solve problems that involve both the ideal gas law and stoichiometry. So reminder, ideal gas law is PV equals nRT. You love it. You'll always love it. And stoichiometry, even more of your favorites, is we're going to be using dimensional analysis to go from mass to mass. And remember, that's where we have to use a balanced equation. All right, so just a couple reminders. Because we're using gas laws, when we see our balanced equations, never ever put solid or liquid data into a gas law. So you cannot use solid or liquid data in PV equals nRT in the ideal gas law. They're not gases. A hint that you're going to want to be doing gas stoichiometry, so using ideal gas law and stoichiometry, is that you're going to see a balanced equation here. You're going to be given a balanced equation. So that'll kind of be a good hint to signify stoichiometry will be involved. And last, we kind of have two different problems we're going to show you. One of them, you're going to use the ideal gas law first, and then stoichiometry. The other one, you're going to first use stoichiometry, and then use whatever you solve there and plug it into the ideal gas law. Okay, so we're going to show you both different versions here. This way. Yeah.
Okay, so I'm going to show you one version where we are. There we go. I'm going to show you one version where we are starting with plugging something into the ideal gas law to solve for the number of moles. And then we are going to use that, use stoichiometry to figure out the grams of potassium chlorate. Okay, so our first example is a sample of solid potassium chlorate was heated in a test tube and decomposed by the following reaction. So it decomposed into potassium chloride and oxygen gas. This is the only thing that we can plug into a gas law because it's the only gas that we have in this equation. The oxygen produced was collected by water displacement, which we saw in our lab, at 22 degrees Celsius at a total pressure of 754 torr. The volume of the gas collected was 0.650 liters, and the vapor pressure of water at 22 degrees Celsius is 21.0 torr. Calculate the pressure of oxygen collected and the mass of potassium chlorate used. So these are the two things that we are looking for. The pressure of oxygen, the partial pressure of oxygen, and the mass of potassium chloride. So first I'm going to solve for the partial pressure of oxygen. And that is just going to be equal to my total pressure, which is 754 torr, minus my water vapor pressure. So 754 torr minus 21.0 torr equals 700, rounded for sig figs, 33 torr. So that is my partial pressure of oxygen. That is one of my answers. That was pretty easy. Now we're going to solve for the mass of potassium chlorate used. Problem. Potassium chlorate is a solid. We can't plug it into our ideal gas law. So what I have to do is I have to plug in for oxygen, solve for my number of moles of oxygen using my ideal gas law, and then do stoichiometry backwards to solve for the amount of potassium chlorate that I used in grams. So quite a few steps involved. I wrote down all my givens here and I underlined them in the appropriate colors. I'm not going to waste time going over it. Pause the video if you need to go ahead and see where all of those came from. But first I'm just going to use you can see that we're solving for the number of moles of oxygen. I'm going to use my ideal gas law to do this. So I'm going to divide by R and T on each side to isolate my variable first. So then I have my number, just bring that down here. My number of moles of oxygen is going to be equal to my PV over RT. P is equal to 733 torr.
Remember, this is the partial pressure of oxygen because we're solving for the partial moles of oxygen.
Partial moles of oxygen. So thankfully, we were already asked to do that. And then times my volume, which is 0.650 liters, divided by my gas constant. I got this off of the periodic table for us, and it's 62.4. Remember, this comes from our unit for,
right,
can you guys see this? The color. Our unit, which is torr times liters divided by moles. What?
Times K.
Oh, yeah. And then my temperature, which is, I already changed this for us, 295.1 Kelvin. Okay? Multiplying this all together, I get my answer to be 259 moles of oxygen. Okay?
Remember, torr is gone, liters is gone. I forgot it last time too. Kelvin is gone.
So all I'm left with is moles. Now, all I got to do is figure out, so now I know how many moles of oxygen were produced, which, using our stoichiometry skills, we can work backwards to figure out how much potassium chloride that means that broke down. So I'm going to go ahead and put this right here, 0.0259 moles of oxygen. I'm going to change that moles of oxygen to moles of potassium chlorate using my mole-to-mole ratio. My mole-to-mole ratio is for every 3 moles of oxygen, I have 2 moles of potassium chlorate. Then I am going to change moles of potassium chlorate to mass. For every 1 mole of potassium chlorate, I have 122.55 grams. Okay? And that gives me grams of potassium chlorate, which is 2.11 grams potassium chlorate. So that is the mass that was of potassium chlorate that was used.
All right. Second example. So that one we started with the ideal gas law, and then we plugged in into stoichiometry, into our dimensional analysis. This next example is the opposite. We're starting with stoichiometry, and then we're going to use the ideal gas law from what we get with our stoichiometry. So we have a sample of oxygen gas collected by water displacement at 22 degrees C and 106 kPa from the decomposition of 24.7 grams of KClO3. Again, the same equation we just saw. Yeah, it is. By a balanced equation right here. The vapor pressure of water at 22 degrees C is 2.2 kPa. Remember, this is from the chart that we can find right here. We can find the water vapor pressure of, I have the wrong one highlighted, but the water vapor pressure of water at 22 degrees C. Partial pressure.
Yeah.
Thank you.
Of water at 22 degrees Celsius, which equals to 2.2 kilopascals.
Now, we're looking for the mass and volume of oxygen gas collected. So here's what we're given. And I just take a look down here for the ideal gas law. We're given some pressures, which we'll figure out in a sec. We know our R, our gas constant, and we know temperature. We don't know V, and we don't know moles. So we don't know volume, which is what we're looking for, and we don't know moles, which is why we're looking for mass. We have 2 unknown variables. That's what tells us that we cannot start with the ideal gas law. We have to start up here with stoichiometry, okay? So let's start up here. We have 24.7 grams of KClO3, so I need grams of KClO3 on bottom, and we're trying to get this into moles, because that's how we go from one substance to another. So, in 1 mole of KClO3, we figured this out in the last one, we have 122.55 grams of KClO3. All right, now that we're in moles of KClO3, we can get into moles of oxygen. Remember, oxygen is the only one that we can use down here in our gas law because it is the only gas, okay? So our mole-to-mole ratio is 3 moles of oxygen for every 2 moles of KClO3, okay? And we're going to figure out the moles. So it is asking for mass, but let's figure out the moles first because we need that down here, okay? So when we solve for the moles, we get 0.302 moles of oxygen. So equals. No, I would just do equal. Yeah. And then you can keep going. 0.302 moles of oxygen. And we can set up, we're going to plug this in right down there. 0.302 moles of oxygen. And then we can just draw our railroad tracks straight from this, okay?
Oh.
I would do under. All right?
I thought you were just gonna...
We're in moles of oxygen, so moles of oxygen goes on bottom. One of the things we're looking for up there in purple is the mass, so we need grams of oxygen on top. For every 1 mole, we have 32 grams of oxygen, that's the molar mass, and we get 9.66 grams of oxygen. All right, so we're halfway there. We've already found the mass of oxygen that is collected. Now we need to find the volume. The only way to find the volume is to use our ideal gas law. Okay, so let's take a look at what we have. Yeah.
I just do want to mention that if we were at STP, you could use stoichiometry, but we're not at STP.
Yes.
So that's the whole point, right? Unless we're at STP, then we have to use the ideal gas law.
That was a good
That's
point.
a mistake that we're going to make. Yeah.
All right, so we're trying to find the pressure of oxygen because, again, if we have the moles of oxygen, we need to be using the partial pressure of oxygen in our ideal gas law. It's either partial pressure of each or it's total of each. Okay, so we have the moles of oxygen, partial pressure of oxygen. All right, so we have 106 kPa is our atmospheric pressure, and the vapor pressure of water is 2.2 kPa. We know that the atmospheric pressure is equal to the partial pressure of oxygen plus the partial pressure of water vapor. Okay, so if we plug this in, 106 equals partial pressure of oxygen plus 2.2 kPa. We get a partial pressure of oxygen of 103.8 kPa. Right? Now, all we don't know is volume. We have our moles, we have our R constant, we have our temperature that I've already turned into Kelvin. So, PV equals nRT. And this time, we're solving for V. So we need to divide both sides by P. Okay, so down here, I'll put it right here and then you can continue. We get V is equal to nRT over P. All right? Now, our number of moles, V of oxygen, this is V of everything, but N of oxygen, P of oxygen. Okay. V is equal to our moles, 0.302 moles of oxygen, times our R value, our gas constant, which is 8.31 kPa, times liters over mole times K. My dog is whining. Our temperature, 295, it's on top.
Oh.
Sorry. 295.1 Kelvin. Okay, and then we're going to divide all of that by our partial pressure of oxygen, which we just found is 103.8 kPa. Make sure you include all the units so that you can see what crosses off. All right? kPa is crossing off. We have moles crossing off, and then we have Kelvin crossing off. So our final unit is liters.
Which is what we want.
Which is what we want for a volume. Okay, that's how you're going to double check you're on the right track. So our volume that we get when we plug all of this in is 7.13 liters of oxygen. Thank you. All right. So, 2 different ways of doing these problems. I know it's a lot. Practice in class. Thanks.